This lecture is about the ideal gas law, PV equals nRT. This lecture is assuming that you already know what an ideal gas is. It's a gas where all internal energy added goes into kinetic energy and thus changes the temperature. So internal energy and temperature are linearly related in an ideal gas. This definition is explained in a previous lecture that I've linked in the description. This lecture is specifically focused on this equation, PV equals nRT, which we call the ideal gas law because it's true for any and every ideal gas. This equation is always true if we're dealing with a gas where the only type of internal energy present is kinetic energy. This video will exist in 3 parts. In the first part, I'll walk you through the meaning of each variable and some tricks to finding them. In the second part, I'll go over some relationships that exist between the variables. And in the last part of the video, I'll conclude with a ton of examples for using this equation in different types of problem solving, whether it's plugging stuff in, using graphs, or using proportional reasoning. This is the meaning of each variable in the ideal gas law. I'm going to go into each one in more detail, but for now you can see that the ideal gas law is telling us that the pressure applied by the gas multiplied by the volume that contains the gas is equal to the number of moles of gas times the ideal gas constant times the absolute temperature of the gas. We know that pressure is equal to the force applied per area along the container of the gas, and its unit is Newton per meter squared or pascals. We covered this in a previous lecture that I'll link in the description, and you're actually expected to remember a lot of properties of pressure from that lecture in order to be able to use the ideal gas law. I'm not going to repeat myself from that previous lecture on all the properties of pressure, so if you haven't watched that previous lecture, you'll want to start there just because I'm going to be using those properties of pressure in some of the problem solving later, and you'll definitely be expected to be able to do that in worksheets, labs, and tests in this course. This is some new information about pressure that you need to know for the ideal gas law. All collisions in an ideal gas are perfectly elastic. Pressure from an ideal gas comes from the impulse of the particles on the container. Because all the collisions are elastic, when the particles hit the container wall, the wall applies a force on the particle, and the particle applies a force back on the wall. So that force on the wall is the force in the pressure equation, and the area is just the area of the wall. So the reason why gas has pressure is that the particles in the gas are constantly bouncing up against the wall of the container of gas, and are thus applying a force on the wall, and are therefore applying pressure on the wall. The next variable to worry about is volume. That's just the 3D volume that the gas occupies. And some problems will require you to calculate the volume of different three-dimensional shapes, so I've left the equations for a few common volumes in the bottom right. The next variable is n, which means the number of moles of gas. As a reminder, there are 2 ways to calculate how many moles are present. You can either divide the mass of the gas by the molar mass of the element, or the number of particles present by Avogadro's constant. So the unit for n is mole, because it's a measurement of how many moles there are. And remember, Avogadro's constant is 6.02 times 10 to the 23rd particles per mole. This just means there are that many particles of an element in 1 mole of that element. I'll give you an example of the 2 ways to find the number of moles in a gas. So if you're given the mass and the element of the gas, as an example, how many moles are in 5 kilograms of oxygen, you would start by using the periodic table to find the molar mass of the element. That can always be found at the bottom of the element's label on the periodic table. So I can see that the molar mass of oxygen is about 16, and that molar mass on the periodic table is always written in terms of grams per mole. So that number means there are 16 grams per mole of oxygen. The second step is to divide the mass of the gas by the molar mass of the element and to make sure that the mass units match. So because this is 5 kilograms of oxygen, I'm going to convert that to grams just so it matches up with the grams in the molar mass. So that's equal to 5,000 grams. I divide the mass of the gas by the molar mass of the element, and when I do that, I find that 5 kilograms of oxygen contain 313 moles of oxygen. So that's how you would find lowercase n if you were dealing with a problem like this with an ideal gas law question. If you're given the number of particles in the gas, you just divide the number of particles by Avogadro's constant, 6.02 times 10 to the 23rd particles per mole. If I wanted to know how many moles does a gas contain if there are 8 times 10 to the 25 particles, I would just divide the number of particles by Avogadro's constant, and I end up with 133 moles. So that's how you find lowercase n in the equation if you have to calculate it. The IB Physics data booklet writes the equation for n like this: lowercase n is equal to uppercase n over uppercase n subscript a. Uppercase n is just the number of particles in the gas, and uppercase n subscript a is Avogadro's constant. And Avogadro's constant is also given in the IB booklet. So you'll never have to memorize that on a test. The next part of the ideal gas law is capital R, and this is just a constant. This is just 8.31 joules per mole Kelvin. It's just a specific relationship that exists to balance out the units that we use. It doesn't really mean anything else. It's just a number that you always have to put into the ideal gas law. The last variable to worry about is capital T, which is the absolute temperature. It's not just the temperature. We call it the absolute temperature because it's only measured in Kelvin, not degrees Celsius or Fahrenheit. An absolute scale is a measurement system where the zero value is where there is actually none of the quantity being measured. So as an example of an absolute scale, if I said I am 80 years old, that means I am 80 years away from being 0 years old, from having no age at all. So that would be an absolute scale, because the 0 point on that scale is where I actually have none of the thing being measured. In comparison, I am 3 years older than before is a relative scale, because at the 0 point of that scale, I am 0 years older than I was before. That doesn't mean I have 0 years of age. It could be at any age where I start. It's totally relative where I start, and I begin increasing from 0 from that point, even though my actual age is not 0. That's an example of a relative scale. The Kelvin scale is an absolute scale, and the Fahrenheit and Celsius scales are relative. What this means is that at 0 degree Kelvin, there is literally no temperature. Temperature is just a measurement of the random motion of particles, and at 0 degrees Kelvin, there is literally no random motion of the particles at all. So the 0 point of the scale is where there is actually 0 of the thing it's measuring. At the 0 point on the Celsius scale, there is still some motion of the particles, so Celsius is a relative scale, so we can't use it in the ideal gas law because the 0 point still has some movement. And you might ask yourself, why is it so important that we use this absolute scale? How does that affect the equation? Well, we can use the math of this equation and what we understand about the variables to understand why temperature has to be absolute. Let's imagine that we have 0 temperature. We don't know whether we're using Celsius or Kelvin. I'm just going to say the temperature is 0. If the temperature of the gas is 0, and I assume that the volume is not 0, it's a normal volume, the only way for this equation to be true is if the left side is also equal to 0. So that means that the pressure must be 0 whenever the temperature of the gas is 0. This has to be true, and if that's not true, if the temperature were 0, but the pressure were somehow not 0, this equation would break down, because it would say a non-zero number on the left is equal to a 0 number on the right. So when temperature is 0, pressure has to be 0 as well. And I remember that pressure comes from particles hitting the sides of the container. And they can only do that if they're moving. If the particles are not moving at all, they're not going to have any collisions with the sides of the container, so there won't be any pressure. So the only way for there to be no pressure is if the particles are not moving at all, which happens at a temperature of 0 Kelvin. So if we use the Kelvin scale for T, that works, because at 0 Kelvin, there is actually 0 pressure because the particles don't hit the wall. If we use Celsius instead, I remember that at 0 degrees Celsius, it is not the case that the particles are standing still. They still have some random motion. And if they still have some random motion, that means that the pressure will not be equal to 0 because the particles will be randomly bumping up against the side of the container and putting a non-zero force on the container, so there will be pressure. So if we say that it's okay to use Celsius for the temperature in the ideal gas law, that would mean that the right side could equal 0, while the left side does not equal 0, and that would cause the equation to not work. So that's why for this equation, we always have to use Kelvin, never Celsius. That's a summary of the meaning of each variable in the ideal gas law. You'll notice that this equation only works when dealing with an ideal gas. The equation itself actually implies that the gas is ideal. Remember that the definition of an ideal gas is there's a linear relationship between internal energy and temperature. I notice on the left I have pressure times volume, and I know that the unit of pressure is a Newton per meter squared, and the unit of volume is a meter cubed. So when I multiply pressure times volume, as I do on the left, I get these variables, which come together to make a Newton meter, which is equal to a joule, which I know is a unit of energy. So pressure times volume actually has units of energy. That's not going to be energy by itself, it's actually going to be some constant, and we don't know exactly what that constant is, but it's not changing the unit at all. So we know that the energy multiplied by some constant that I don't understand is equal to nRT, and if we assume the amount of gas is staying the same, n times r is also a constant, and I'm left with a linear relationship between the energy and the temperature. It literally fits the linear equation y equals m times x. So because this is linear, this is definitely an ideal gas, and because it's an ideal gas, it's linear. That's why this equation only works when we're dealing with an ideal gas, because if we were working with a non-ideal gas, some of that energy would go into breaking the bonds between particles, and it wouldn't affect the temperature, and the left side would get a different value than the right side. And this is also the reason why we care about whether a gas is an ideal gas. This is why we came up with that definition of an ideal gas. If we model a gas as ideal, we are allowed to use this equation to predict the gas's behavior, and we can do that better the more the gas behaves like an ideal gas, the more it fits this equation. A lot of questions come up about graphing different parts of the ideal gas law. Because there are so many variables, we usually hold some of them constant and graph other variables. For all three of these graphs, I'm going to pretend that lowercase n is a constant. The amount of gas being graphed is remaining the same. If I construct a graph of pressure versus time and I hold the volume constant, I can predict what that graph will look like using the equation itself. I've written all the constants in black, So when I rearrange this equation to get the y value on one side and the x value times a constant on the other, I can see that this fits a linear pattern where pressure is the y value, temperature is the x value, and the slope is nr over v, and the y-intercept is 0. So this fits a linear pattern, and this is what that graph would look like as a result, and this would be the slope. So what this graph is physically showing is a situation where we are holding the volume constant, but increasing the temperature and observing what happens to pressure. And if we increase the temperature of the gas in the container, those particles are going to get faster and faster because temperature is a measurement of the average kinetic energy of particles. And if I make the particles go faster by increasing the temperature, they're going to hit the walls of the container harder and make the force bigger on the container and therefore increase the pressure. So as I go up this graph, you can see that as I increase the temperature, the force increases and therefore the pressure on the walls increase. So that's what that graph is physically showing us about the gas. We can also hold pressure constant and make a volume versus temperature graph. Rearranging PV equals nRT to get V on one side, I get this equation, which I can see also fits a linear form, where the slope is nr over pressure, and the y-intercept is 0. So I'll draw that line out. So this is the slope of that graph. And to build your intuition here, what's happening here is that I'm increasing the temperature, but while I'm doing that, I'm trying to change the volume in the exact way that keeps the pressure constant, because we're holding the pressure constant in the second example. So because pressure is equal to force over area, I know that the force of the particles hitting the wall will increase when I increase the temperature because they'll be moving faster. So in order to keep pressure constant, I'll have to increase the size of the area they're impacting as well. So if I start with a low temperature and low volume, and then increase the temperature while holding the pressure constant, I have to increase the area that they're impacting as well, and so the volume increases. That's what that second graph is showing us. On the third graph, we're holding temperature constant and graphing pressure versus volume. So when I write this out, PV equals nRT and isolate P, I can see that this actually fits an inverse form because this is measuring 1 over x. So this graph is an inverse shape like this. This is showing a situation where the pressure starts off very high and we're keeping the temperature constant. We're not increasing the velocity of the particles. If we don't increase the temperature, that means the force applied by the particles will remain constant as well. And if we increase the volume, the area that they impact is going to become larger. So if we hold F constant and make A larger, you can see that as a result, the pressure shrinks, just like it shows it doing on the graph. So as the volume increases, the pressure decreases, as long as we're holding the temperature constant. One last note about graphing, if we did measure temperature in degrees Celsius, 0 degrees Celsius would still have a non-zero pressure because the particles would still be moving. So a pressure-temperature graph with Celsius as the unit of temperature would look something like this with a non-zero y-intercept. Because at 0 degrees Celsius, there would still be a non-zero pressure. This is the last part of the video where I'll do example problems in graphing, math, and proportional reasoning. These are 2 example graph problems. An ideal gas of constant mass is held at a constant pressure P. This graph shows the volume V of the gas as it varies with constant temperature T. What is the slope of the graph? Well, I know PV equals nRT, so isolating the y and the x, I can see that they fit this form. So the constant taking the place of the slope is nr over P. That would be the slope of the graph, and that's the answer to the question. Example number 2 says the graph below shows the pressure of a gas on the y-axis and the inverse of the volume on the x-axis. The graph is at a constant temperature. Determine the slope of the graph, including the correct unit of slope. We'll start with part A, determine the slope of the graph, including the correct unit of slope. I know that slope is rise over run. I can see 2 points on the graph that I'll compare. That's the slope of the graph. I just read the numbers and units off of the graph. And I remember from a previous part of this lecture that a Pascal times a meter cubed is equal to a joule. The reason why is that a Pascal times a meter cubed is equal to a Newton over meter squared times meters cubed, which is equal to a Newton meter, which is equal to a joule. Part B says the temperature of the gas is 330 Kelvin. Determine the number of moles of gas present. So PV equals nRT. Rearranging this to get the equation for the graph, I can use this to isolate the parts of the equation that go with the slope, because v to the negative 1 is my x-axis and p is my y-axis. I can see that the slope must be equal to n times r times t. So n is equal to the slope over rt. I can plug in what I know about the slope. R is always a constant, and 330 Kelvin I get from the problem. And when I calculate that out, that's equal to 18.2 moles of gas present based on the properties of this graph. These next 2 examples are math problems instead of graph problems. In example 1, 20 kilograms of argon gas is heated to a temperature of 30 degrees Celsius. If the gas is contained in a cylinder of radius 2 meters and height 0.5 meters, what is the pressure of the gas? I don't even think about it, I just start writing down what I know. The volume is the volume of a cylinder, so this is the equation for that. So the total volume is 6.3 meters cubed. To calculate the number of moles, I can divide the mass of the gas by the molar mass, and I can see that argon has a molar mass of about 40 if I look at the periodic table. So that's 40 grams per mole. So to make this convertible, I convert the mass into grams instead of kilograms. And when I do that division, I find that there are 500 moles present in this gas. R is always that same constant no matter what. And T is 30 degrees Celsius, but I need that measured in Kelvin. So I add 273 to get 303 Kelvin. To find the pressure, I just use the equation and isolate P, so I divided both sides by V. And when I plug in all the numbers that I have, I get a pressure of 2 times 10 to the 5th pascals. So that's how you would solve the math problem using PV equals nRT. Example 2 is more complex. For example 2, I'm going to be using some of the properties that we learned about in the pressure lecture. So again, definitely refer back to that in the description of the video if you haven't watched it yet. The air in a kitchen has pressure 1 times 10 to the 5th pascals and temperature 25 degrees Celsius. A refrigerator has an internal volume of 0.36 meters cubed. The door of the refrigerator is closed and the air inside is cooled to 4 degrees Celsius, and the number of air molecules stays the same. In part A, when the door is open, the air inside the refrigerator is at the same temperature as the kitchen. Calculate the number of air molecules in the refrigerator. I know that the pressure inside the refrigerator is the same as outside when the door is open because pressure is always equal when there isn't a barrier between the two gases. The volume of the refrigerator is 0.36, and the temperature is 25 degrees Celsius, which I need in Kelvin, so that's 298 Kelvin. And I need to know lowercase n before I can calculate the number of air molecules. And R is always that same number. I can plug that into PV equals nRT, so n is equal to this equation. And when I plug in my values, I get 14.5 moles. But I need to know how many particles there are. So the number of moles is equal to the number of particles over Avogadro's number. So when I multiply both sides by Avogadro's number, I get a number of particles equal to 8.73 times 10 to the 24th. That's how many particles of air there are in the refrigerator. Part B says to calculate the pressure inside the refrigerator after the air is cooled. So we're dealing with a new temperature. We know the volume is the same. The temperature is now 4 degrees Celsius, which is equal to 277 Kelvin, and lowercase n is 14.5 moles. There's no air leaving the refrigerator after the door is closed, so we can use that same answer from part A. R is the same, that's always that constant, and we're trying to find the pressure. So I'll rearrange the equation to get pressure by itself, and plugging in my numbers gets me 9.27 times 10 to the 4th pascals. Part C says the refrigerator door has an area of 0.8 meters squared. What is the minimum force needed to open the door? You'll remember from the pressure lecture that we need to understand the force on both sides of the door before we can understand how much force it takes to open the door. The pressure on one side, the outside, is 1 times 10 to the 5th pascals, and on the other side from the previous answer is 9.27 times 10 to the 4th pascals. Rearranging the pressure equation gets me force equals pressure times area. So the force from the outside is 8 times 10 to the 4th newtons, and the force from the inside is 7.42 times 10 to the 4th newtons. So the force required to open the door, as you'll remember from the pressure lecture, is the difference between those two forces. So the difference between those two forces is going to be equal to 5.8 times 10 to the 3rd newtons. So that's how much force you would have to apply to open the door of the refrigerator after it had been sealed and the air had been lowered to that lower temperature. Finally, I'll close out with 4 proportional reasoning problems. I'm doing more of these just because they're a very common type of test question. In example 1, 2 containers A and B contain an ideal gas and are connected with a tube of negligible mass. The volume of A is 3 times that of B. A is at a temperature of 100 Kelvin and B is at a temperature of 400 Kelvin. What is the ratio of the mass of gas in A to the mass of gas in B? To start off, we know that because the gases aren't moving between the containers, that their pressures are the same. Because gas always flows from a high pressure to a low pressure area, so if that's not happening, the two pressures must be equal. I know the temperature of A and the temperature of B, and the volume of A is 3 times the volume of B, and I can use PV equals nRT to relate these. And I'm trying to compare the mass, which I know has something to do with the number of moles, so I'll rearrange to isolate the number of moles. The number of moles in A is equal to this, and the number of moles in B is equal to this, just based on the variables that I have. I know that the number of moles is equal to the mass over the molar mass, so therefore the mass by itself is the number of moles times the molar mass. So this is the mass of A, and this is the mass of B. And this is the ratio between them because that's what we're trying to find. And the molar masses are the same because it's the same gas, so it's the same element. So that means I can cancel out the molar mass, and I'm just left with Na over Nb. So Na over Nb is equal to the mass of A over the mass of B, so that will be the answer to my problem if I can write that out as a number. So I rewrite that using the equations I have for Na and Nb, And I'll write those equations entirely in terms of the variables for B. I know that the pressure of A is equal to the pressure of B, and the volume of A is equal to 3 times the volume of B, so I can replace those. And I also have 1 over 100 over 1 over 400, which is just equal to 4 in the numerator. And I can now cancel a bunch of stuff out because there's a lot that appears in the numerator and denominator, and when I cancel that out, I get a final answer of 12. So the ratio of mass A to mass B is 12. There's 12 times as much mass in container A as in container B. In example 2, a tank of fixed volume V contains n molecules of an ideal gas at temperature T. The pressure at Kelvin temperature T is 30 megapascals. N over 3 molecules are removed, and the temperature changes to 2T. What is the new pressure of the gas? As an answer, the original pressure, P1, is equal to these values, and I know that's equal to 30 megapascals. Pressure 2 has 2/3 of the molecules of pressure 1, and the temperature is twice as high, so I've written those values in. If I can isolate my original values in that new equation, I'll understand how the new pressure relates to the old pressure. So if I bring up those numbers, if I bring up that 2 to one side, I get 4/3 times those original values. So that means this is equal to 4/3 times P1, which is equal to 4/3 times 30 megapascals, which is just equal to 40 megapascals. So that's the new pressure of the gas. In example 3, container A contains 2 moles of an ideal gas, and container B contains 4 moles of the same ideal gas. B has 5 times the volume of A. The pressure in A is 2 times the pressure of B. What is the ratio of the temperature of gas A to the temperature of gas B? So as an answer, PV equals nRT. I'll isolate T by itself because I'm taking the ratio of temperatures. I know that the number of moles in A is 2, and the number of moles in B is 4. And the volume of B is 5 times the volume of A, and the pressure of A is 2 times the pressure of B. So this is the equation for the temperature A, and this is the equation for the temperature B. So TA over TB is equal to this. And I can now rewrite some variables as other variables and start to cancel things out. So I know that PA is equal to 2PB, so I'll just replace all the A's with B variables. Because VB is 5VA, VA is equal to 0.2 VB. And I know that NA is 2 and NB is 4, so if I take 1 over 2 over 1 over 4, I get 2 in the numerator as a result. And when I multiply those out and cancel out the variables, I get 0.8. So that's the ratio of the temperature of container A to container B. Finally, in example 4, a fixed mass of an ideal gas in a closed container with a movable piston initially occupies a volume V. The position of the piston is changed so that the temperature of the gas doubles and the pressure remains the same. What is the new volume of the gas? PV equals nRT, and I want to understand the relationship between volumes, so I start by isolating that. The amount of gas is the same, so the moles are the same. The new temperature 2 is double temperature 1. The pressures are the same. So now I can compare V1 and V2. And the problem just refers to this original volume as V. This is V2. And I can rewrite the V2 variables in terms of the V1 variables. The number of moles are the same. T2 is equal to 2 times T1, and the pressures are also the same. I can now isolate my equation for V1 by itself, so I get 2 times that equation for V1. So that means that the new volume is twice as large as the original volume. That's how you do proportional reasoning problems, and that's how you do all types of problems that appear in IB for the ideal gas law, PV equals nRT.